Okay, so yeah, this is where we left off, and I cleaned it up nicely for us. So here again, let's just talk about what data represents. So if we start with the Boolean, it's just on-off, light switches, positive, negatives, 0 or 1, or the proper term here is we have binary data. Binary means it's in 2 states. Okay? If we move to integers, as you can see here, the way we represent binary when we're talking about decimal numbers is somewhat unknown at this point. We got to 0, 1, 2, 3, but how do we get to stuff like 197? We're going to learn a system for that. When we talk about doubles, well, it could use the same system, especially if we split apart the decimal and the whole number portion. That will be a way to do it. Okay? What about characters? Well, as you guys have already seen, characters are also binary numbers, just in a lookup table called the ASCII table. Strings are arrays of characters, so that's okay. And then classes is just an organization of all the primitive data. So in reality, everything is based on Booleans, on binary data. But this is the part that we kind of need to focus on. How do we make a conversion from one system to another? Okay, that's what we're going to learn. As I said, this is in the curriculum right there. The one that's missing that we didn't talk about was colors. But colors, if you think even in Java, is a class. So it's a class, so it is also built up from that data. So just some theory to get started. You live in an analog world. Your world is not binary. Right now, hearing my voice, you hear different tones of various levels. It's not just ones and zeros coming out of my mouth. It is a variety of tones. When you look at me, or you look at the projector, or you look around the room, when you see colors and shapes and objects, that's also a variety of data. It's not just black and white. It's not just on and off. That's an analog world. But the computer, as we just saw, is a digital world. So we have to be translating between those two worlds all the time. Okay? For example, when you watch a movie, you know you're actually not, what you're watching is a series of images being flipped in front of your eyes really quickly to give the appearance of moving pictures. That's why it's called moving pictures. Okay? We accept that. We accept that that is happening. Okay? We don't know where one picture stops and the next begins because that's the way our brains interpret that data. When you look at a picture on the internet, you know you're looking at individual points of light that are just being blended together with your eyes, and you're accepting it, and here's a term from the 40S course, as an abstraction. Okay? So, our perception of the world is an analog world using abstract data. Okay? Analog data is a wavy line that moves often at predictable rates. Okay? But what's happening in the computer is a digital world of discrete on-off values. Digital is the reality to the computer, and that's why it works so well, because it's so simple. Okay? So those on-off, true, false, black, white, 1, 0 data values, those states are important to the computer. Okay? But we don't live in that world. So the translation between it is what we need to do as programmers to translate the world of digital and the world of analog. Okay? On the hardware side, there's actual devices built into some of this stuff called an ADC or a DAC chip. Okay? The analog to digital converter or the digital to analog converter. Okay? Analog signals are read by these hardware devices and then changed into digital signals. So sound, light, temperature, all those values fall in a continuum. I'm sure over your course of the 12 public school years, you've graphed things like temperature values. And you know what the graph looks like. It's not an on-off graph. It's something like this, a wave, right? Or a wavelength. If any of you use like those in physics class, like, what do you call them? So it's a meter that puts that on a visual, never mind. Not a sine graph. Okay. Now, if we were to graph digital signals, it's not like that. Digital signals has a very discrete on-off signal base. Okay? There is no in-between. There's no in-between with the on-off signals. It's just off or on. So here you can see Zeros represent the off state, ones represent the on state. That's how you could interpret that data. Okay? Another simple way to look at it is an analog versus digital clock. That clock is analog. If I asked you what time it is, in a lot of ways, it's kind of in between. But when you hit a digital clock, it's always set on a specific time at a specific moment. Okay, so those converters do those conversions from the hardware side. Okay, I'll use a example, a microphone. Okay, or something like a photosensitive diode, which is used to photosensitive diodes are react to light, so that they can produce energy based on the amount of light hitting it. More light produces more energy. Then they have specific diodes for specific colors. So if a specific wavelength of light hits it, a specific amount of energy is generated. But microphones, the way they work, is they have metal plates that vibrate when sound waves hit them. The more they vibrate, the louder the sound. So it produces a wave of sound, which is then translated into a voltage of current. But that voltage of current is a wave, right? How much current is not just on-off, but it's a variety of voltages of current. So we need to take that analog voltage signal and convert it into binary data. It does this through a process of sampling, which we'll get to in a second. Again, the photodiodes is the energy with light. The stronger the light, the stronger the electrical signal. Okay? Computers have to work with the digital. So on the other side, when we go out of a computer, we have all this 1-0 data. That 1-0 data has to be translated back into voltage levels for things like speakers and monitors. So that uses a DAC conversion process, digital to analog. Okay? The way that works, depending on the device, is it can do things like go through a matrix of resistors. Again, if you've studied some electronics or you've been in physics class, you know what a resistor is. That's not necessary for the IB curriculum, but basically it generates an analog stream coming out of the computer. Okay. Now, how it does this is through a sampling process. And the precision of the sampling affects the accuracy of the conversion. So here's an example. The more sampling, the better the conversion. So let's say this was the data we got. We got various, say it was a microphone. We got this much voltage, then we got this much voltage, then we got this much, et cetera, et cetera, et cetera. Okay? If that's how much we sampled that analog data, we could generate a bit of a wave from it. If we sampled it more often, we'd get a more accurate representation of that analog data. What's the plus side of more sampling? Well, I'll give you the plus side. It's more close to the reality of the analog world. What's the downside of more sampling? More data, okay? And depending on the system that we are a part of, we may not be able to handle that much data. It may be unusable because of the amount of data. We talked a little bit about that yesterday. So there's always a fine line between how much data do we get to sample it accurately versus how much data we can actually handle. Okay, so now we're going to go into units. We've talked about this before. Binary digits is the root of the word bits, and it's that discrete concrete value between 1 and 0 or on and off. The computer will generate ones and zeros, or these bits, based on other values. For example, an integer like 28,485 will be converted into binary data, and I'm going to show you how to do that. That's coming up. Okay? A byte is 8 binary bits. Okay? So 1 byte is 8 bits. Okay? To think in terms of what could a byte of data store, you could think of it like 1 character. That's why the ASCII table uses a byte value. It can store about 1 letter or 1 character. Okay? A kilobyte is 1,024 bytes. And I asked you guys yesterday why it was that number. Well, it's that many bytes, which is 8 bits, okay? And the kilobyte is because it's represented by 2 to the power of 10, because we're working in a base of 2 values, not 10 values like you guys are used to, okay? That's approximately 1 page of text, a kilobyte. That's approximate. Then we move up to the megabyte, which is 1,048,576 bytes, or 2 to the power of 20, okay? Megabyte can store about a book worth of data, right? Like a novel's worth of data. Okay, so now we're moving into the megabyte. Then we can go to the gigabytes, which is now beyond the millions into the billions. Now, why is it that number? What's a better way to represent it? Think back to here. 2 to the power of 30, right. Okay, so that's equivalent to like a shelf of books in a library. Okay, and you guys know gigabyte is now the storage unit that you're probably the most comfortable with in your computer experience, right? Moving up from that, we can go to terabyte if we want. But here's the general way, and then from there we can go further. Maybe I should update this, right? Bit, byte, kilobyte, megabyte, gigabyte, right? 2 to the power of 10, 2 to the power of 20, 2 to the power of 30, okay? So it's moving up in powers, or exponentially, but based on a different base than the one we're used to. We're a base 10 system. Now, that's a unit of storage, a bit, okay? Sometimes they use the symbol B, lowercase b, okay? The byte often uses the uppercase b. Again, that's not in the IB curriculum, but just, I actually saw it in the side notes in the curriculum, okay? When we're talking about speed, that's not a unit of storage. That's a unit that describes how many instructions a computer can carry out in 1 second of time. And that's measured in hertz. Okay? Cycles per second. What are cycles? Why, that's the machine instruction cycle. So how many times can it go through that machine instruction cycle in 1 second would be a unit called hertz. So if you had a 1 hertz computer, it could go through the machine instruction cycle once every second. But we don't measure it in that way. No one's buying a 1 hertz computer. Okay? The Pentium 3 processor back in the 90s clocked in at around 500 to 700 megahertz, okay? Which was 500 million operations per second. What's the speed of, say, a modern computer right now in hertz? Someone go online, find a Best Buy page right now, find a... Okay, and we're not talking megahertz anymore, are we? Gigahertz, right? So the speed units have also moved to that. So you guys have grown up in an era where probably when you were younger, the units were being measured in megahertz. Now you're used to them being measured in gigahertz. What will your children be measuring their computer speeds in? What will your grandchildren be measuring their computer speeds in? Okay? In inches, yeah. Well, the world will collapse and there'll be no computers. All right, so here's some terminology again from tera, giga, mega, kilo, centa, milli, micro, nano, pico, which goes the other way, okay? And the various symbols that are often used for that. Notice the capitals sometimes appear, the lowercase, and then that, anyone know that one? That symbol, the U with the little hangy on it, means micro. Seriously, you teenagers haven't seen that in, for example, the software package uTorrent, which uses that symbol? Okay, yeah, of course you don't. No, of course you don't. Of course you don't download stuff. Anyways. All right. So kilobyte, megabyte, gigabyte, terabyte, or we can move into hertz, okay? We can move into units of speed or units of storage. And again, it's not in nice round numbers like the 1000s, but more like the 1024s, because it's measured with 2 to the power of as a base, not as 10 to the power of, like you'd see in scientific notation, okay? So a storage device of 8 gigabytes is the equivalent of 8 billion, et cetera, characters, okay? Or 1 billion words or 5 million pages of data. These are huge amounts of data that the human mind has a lot of trouble grasping. They say that about things in the United States when they say their deficit is in the trillions. Like that unit of measurement is so ginormous that your average person can't actually grasp how big it actually is. It's huge, that's right, okay. All right, so let's do the conversion from one base to another. That's the key. Now, I'm going to show you several different ways to do this, but let's start with something very simple. We've already done a little bit of this, okay? So over here, we're going to have our decimal numbers. So this is the way we count normally. Over here, we're going to have our binary numbers, okay? But before we even do binary, let's go back to when you first learned about numbers in general. You were like, okay, well, my teacher taught me 0. Actually, 0 wasn't the first number you were taught. 0 is a concept that comes in later. And actually, if you look all the way back into your grade 9 math notes, you'll see that grade 9 math we teach that there's a set of numbers called the natural numbers, which starts at 1. Because that's the natural number you start with. Some cultures don't even have 0 in their number sets. Then you got to 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there was a bit of a problem. Those are the 10 digits we use. In order to move to the next number, what do we have to do? We have to move to a new place and reorder these digits to do this. We're still using the same set of digits, but now we're taking up another place. So I want you to keep that in mind, because now we're going to go over here to binary. 0 is 0. 1 is 1. 2 is not a digit we can use. So just like the problem we encountered here, we have to now reorder the digits. So the representation of 2 is 1, 0. The representation of 3 is 1, 1. Okay? How do we represent 4? We have to move to the next place. Right. Now, what that means as well is that if I look back here, there was probably a 0 there. Just like there would be here, right? This is really like this. It doesn't really matter. We tend to ignore it, but that's okay, isn't it? Now, what happens when I get all the way up to 99 and then I go to 100? Okay, I can do that. I have to reorder the digits. But there was zeros there as well, right? Does that make sense so far? There's essentially an infinite number of zeros on the front there. Right? Can we use infinite terms on a computer? No, we have to set a limit. So let's set the limit right now to 2 digits. Okay? So we'll say you can represent numbers, but you only get 2 digits. Can I count to 4? No, I can't. I can't count to 4. Can I count to -1? Well, no, because I've already used up all the sequences there. Unless I say you get 3 digits, but the first digit represents the sign. Okay? So these would be unsigned binary numbers. What if I signed them? Not like with my signature, but like, okay. So now I'm going to give you 3 slots to work with. Okay? 0 will be 0. 1, on the positive side, I should pick a state. So let's say 0 represents a positive number. So then this is 1. That's positive 1. This can be positive 2. This can be positive 3. Now I could represent negatives as well. So if I move this down, I can go, okay, 0, 1, 1, 0, 1, 1. But if I put a 1 on front, these will become negative, whereas these become positive. And what sign is 0? First of all, answer like a good math student. What sign is 0? Forget you've ever learned computer science in your life. What sign is 0? What does every math teacher tell you? It's neither. It's unsigned. It has no sign. Can you give that to the computer? Will it accept that logic? Nope. It needs a sign. According to the system we just came up with, it looks to be positive. Which, if you didn't have math teachers in your life, if you didn't have me in your life, single tear, and I just asked you, what sign is 0? Without thinking, what would you intuitively answer? So there are some outliers, but generally, most people also feel 0 is positive. Because think about when you write it in math, you usually don't write a sign in front of it either. You assume it's positive, right? So in a lot of ways, this representation makes sense. But so how high can I count in a 3-digit system if I allow for negatives? I can count from 0 to positive 3, and from 0 down to negative 3. How many positive numbers do I have? No, look again. 4. How many negative numbers do I have? 3. Notice one more on the positive side. Do you guys remember a question all the way back in grade 10? When I showed you, actually let me take a second to just quickly prove this. If I go all the way back to the grade 10 computer science notes on variables, I'm just going to open this instead of opening the whole thing. Okay? And I go all the way, you guys remember this when you first learned about variables, and I went to this slide, and I showed you that integers in C# had a range. So that was the first thing you had to grasp, that didn't go on forever. But notice, this goes to 47, this goes to 48. What? It's counterintuitive. Why is there one more on the negative side? In the system we just came up with, there was one more on the positive side. Okay? It has something to do with 0. You're right. But the system of representing positives and negatives is not as simple as adding a 0 or a 1 at the front. There's a different system for it. Oh, look, the hands went away. Yes? That's not cool. That's true, but that's not the reason why. So the 0 is counting as a positive number, but the reason for that is not as simple as you'd think. Okay, so let's forget about negatives for a second. Let's go to 3 digits. Okay, so right now I've been able to count to 0, 1, 2, 3. Let's count to 4. You guys already told me what it was. What was it? 1, 0, 0. Let's count to 5. 1, 0, 1. Let's count to 6. 1, 1, 0. At this point, I might actually tell you that this is not hard. If you're thinking, how are they coming up with those numbers? You're just counting normally. But you're counting with only the digits you know that are allowed to you. Watch. 1, 10, 11, 100, 101, 110. What's the next one allowed? 111. What's the next one allowed after that? I can't go to 112. I can't go to 113. Whoops, pardon me. The next number I can actually count to is 1,000. What's the next number after that I can count to? 1,001. Then, keep going. What's next? 1,010. Then what? 1,011. Now what? Yeah. 1,100, no. 1,101. Running out of space. Extend page. Whoops. Extend page. What's next? What's next? 1,110. And then, what's next? What's next? We now got to go to the next digit. Okay? Now, let's backtrack for a second. Let's fill in missing zeros to the front of these ones. Okay? And then I got to move this up. Let's add the zeros to the front of this one. So I got to add zeros here and zeros here. Oops. Okay? We got a binary system. Did you see what it counted to, by the way? You weren't paying. I stopped saying what number it counted to. Is it 15 or is it 16? Well, let's track it. Hang on, let me get rid of these. Actually, let me make this a little bit smaller so it fits on the screen. Okay, so let me use black for this. Okay, so let's count these. People in the hallway are saying, wow, they're counting. What a complicated class that is. Okay, count with me. No. You guys are pathetic. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Congratulations, Brody, when you should be doing your work instead of paying attention to me. Very good. 15. How many binary numbers are there right there? Think? 16, right. Okay. Now, if that counting system was difficult for you, watch this. Track just this digit going down. Tell me the sequence. Move to the next digit. Tell me the sequence.
1 0 0 1 1 0 0 1 1.
Move to the next digit. Track the sequence.
0 0 0 0 1.
Okay, instead of just saying that, tell me the sequence.
4 0 0.
4 zeros, 4 ones. Move to the next one. What's the pattern?
8 0 8 0.
Predict what the next pattern will be.
16 0 16 1.
You got it. So it goes up by 2, 4, 8, 16. What would the next one be?
32.
Yeah. Yeah, you guys got it. That's the sequence. It's okay. Hang on, let me pause my video. I'm recording this right now.